Okay, so last time we did an example using the integral method, and we stuck with the momentum form of the integral equation, and we got the friction factor. This time we'll move on to doing the same steps, but we'll do a problem involving the thermal form of the integral equation. So we'll be getting things like the heat transfer coefficient and the Nusselt number. So we're going to again attack a problem that we know the answer to. It's a simple problem. There's obviously correlations for this. There's an exact solution for flow over a flat plate. This plate has a constant surface temperature. There's nothing interesting going on here. There's a laminar boundary layer that forms. There's no transpiration. We're going to assume that viscous dissipation is not very important. And so this is the sort of self-similar solution that you can look up in pretty much any book. So we're gonna solve this using the integral method. The steps are pretty much the same as what we talked about last time. So we'll assume a functional form for temperature instead of velocity. We'll substitute that temperature distribution into the integral form of the boundary layer equation after we simplify it for this problem. So there'll be a bunch of terms in that equation that go away. And if we do the integration, we should end up with an ordinary differential equation that tells us how the boundary layer thickness grows with position. We can solve that boundary layer ODE. So we'll solve for the boundary layer thickness as a function of x. And that boundary layer thickness will govern the things that we really care about, like the heat transfer coefficient or the heat flux or the Nusselt number. Okay, so here's the integral form of the energy equation. We talked about how this came to be the other day, and we talked about what these terms mean. This is the rate of change of the enthalpy carried by the boundary layer, and this would be related to energy injected into the boundary layer due to transpiration. So this is the velocity in the y direction at y equals 0. It's going to be 0 most of the time, but if you have either suction or some kind of transpiration going on, that might not be 0. This is energy injected either by conduction at the surface or conduction at the outer edge of the boundary layer, right? So typically that's conduction at the surface is important. Conduction at the outer edge of the boundary layer usually is 0, just like the shear stress at the outer edge of the boundary layer is 0, but we'll leave that in there. And then this is viscous dissipation. So for this particular problem, there is no transpiration, so we don't have to worry about this term. That term's going to go away. There's no energy being conducted at the edge of the boundary layer, so that term's going to go away, and we've decided that viscous dissipation is not important. That should probably be justified by calculating the ratio of the accurate number to the Reynolds number, finding that it's really small, but that would go away. So we're only left with the rate of change of the enthalpy carried by the boundary layer being equal to the rate at which we're conducting energy into the boundary layer at the surface. So these two things have to balance, and that's our integral form for this particular problem. Okay, so the next thing we have to do is think about what temperature distribution we want to assume. So this is a laminar problem, and as a result we need a nice smooth temperature distribution that goes from Ts at y equals 0 out to T infinity at y equals delta T. And so polynomials are nice and smooth. They're an appropriate choice for this kind of a problem. They would not be an appropriate choice if we had a turbulent boundary layer. For a laminar boundary layer, that'll work. I chose here a second order polynomial just to be consistent with what we did last time in terms of our velocity distribution. So I have, again, three different coefficients that I get to choose. And you sort of do the same kind of thing we talked about last time with the velocity distribution. If I can choose these three coefficients, I'm going to make my temperature distribution do as many logical things as I can. So one thing it needs to do is at y equals 0, it should give me the surface temperature. Another thing you'd really like it to do is if you go out to y equals delta sub t, you'd like to get back to t infinity. And then if you still have coefficients left, some other things you could make it do are give you the right heat flux at the outer edge of the boundary layer. So for us, the heat flux, the conduction heat flux at y equals delta sub t should be 0. If you can keep going, which we obviously can't since we only have 3 coefficients, you could make the differential x momentum be satisfied at different locations. So here we could satisfy it at the surface, which would for us tell us that the second derivative needs to be 0 at y equals 0, and we could keep going. But these 3 would be enough. We showed how to do this last time with the velocity distribution. It's no different really for the temperature distribution, and you end up with actually functionally the same form of the temperature distribution. So here's the temperature distribution we're going to use. Just like with the velocity distribution, these have been done for you, right? So for a laminar boundary layer, if you want to go from linear to second order to third order, these are the temperature distributions that you could select from. You don't have to derive them yourself. Linear is just, obviously a linear temperature distribution. Second order, this is what we just derived, right? If we set this heat transfer rate at the outer edge of the boundary layer to 0, we get exactly, what we have here. In third order, it gets more complicated, but you could use that to get even better results. Just like the velocity distribution, as you choose higher order polynomials or more sophisticated temperature distributions, you're going to get closer and closer to the exact temperature distribution. So our second order is a pretty good compromise between complicated math and accuracy, right? So that's what we'll use here. Okay, so here's our temperature distribution. When we had our velocity distribution, we said that once we've selected a velocity distribution, then the shear stress at the surface of the plate is related to the boundary layer thickness according to what our velocity distribution is, because it's related to the gradient of the velocity at y equals 0. And it's the same thing for the temperature distribution. Once we've selected a temperature distribution, then the heat flux at the surface of the plate is related to the temperature distribution according to Fourier's law. So if I want the heat flux at the surface of the plate, it's minus k dt dy at y equals 0. If I take this temperature distribution and substitute it in here, then this is what I have. So minus k times d dy of, let's see, t infinity minus t sub s, and then this group right here. T infinity and ts theoretically could change with x for sure, right? We could be doing some problem where those things are changing. They can't change with y, so I can pull them out of this derivative with respect to y, and then I'm just taking the derivative of this at y equals 0, and that becomes 2 over delta sub t. So the heat flux is related to the boundary layer thickness, the thermal boundary layer thickness, according to this equation here, right? And that's actually kind of important, because the boundary conditions that you can get in a problem can either be the surface temperature might be given to you, either it's a constant or maybe it's a function of x, but there's also problems where the heat flux might be given to you. Maybe the heat flux is some prescribed function of x. So you can go back and forth between the heat flux and the surface temperature with this equation right here, right? If you want the heat flux in terms of the surface temperature to free stream temperature difference, that's just this equation here. If instead you want the surface to free stream temperature difference in terms of the heat flux, well, that's this equation here, right? So we can flip back and forth between them. So here's our momentum equation. Again, we had simplified it down to the terms that were relevant for this problem. This is the rate that enthalpy is carried by the rate of change of enthalpy carried by the boundary layer. And then this is the heat flux, so the rate we're injecting energy at the surface. I have to now do my substitutions. So let's see, over here for the heat flux, I'm going to plug in the equation we just derived, right? So that'll go here. And then for this temperature here, I'll plug in my temperature distribution here. U, you have to remember, U is not a constant, right? If I'm integrating with respect to y from the surface of the plate to the boundary layer thickness, U is going to go from 0 to U infinity in some way, right? So here for U, I got to plug in my velocity distribution that I'm going to use, and I'm going to use the same one that I used last time, right? I'm going to use that second order polynomial. So I have to make these substitutions into here, and that gives me this, right? So if we go through this, you can see where these things come from. This substitution gives me this. For t, I'm plugging in, let's see, what is t? T, according to this equation, is Ts plus T infinity minus Ts times this, and that's what I plugged in right here. And then for U, I have U infinity times this group right here, so U. So this is, I guess, the equation I have to solve. This is the integral I have to do. Right, so let's see. When I do this integral right here, so let's go back and look at this. When I made this substitution right here, I actually implicitly made an assumption. And it's easy to forget this, but I'm integrating here from 0 to delta sub t of U and then of the temperature, right? So the U that I have to put in here, the functional form of U as a function of y that I put in here needs to be valid all the way from the surface to the outer edge of the thermal boundary layer. And the functional form that I did put in here, right here, this is valid from the surface, but only to the outer edge of the momentum boundary layer, right? After I get beyond the momentum boundary layer thickness, my U is no longer changing, it's U infinity, right? So this integral, as I've set it up right here, is only going to be valid for the case where the momentum boundary layer thickness is larger than the thermal boundary layer thickness, right? So all the time that I'm inside the thermal boundary layer doing this integral, this needs to be the right velocity distribution. And if you remember what we talked about in terms of Prandtl number, fluids without large Prandtl number are going to have a large momentum boundary layer thickness, larger momentum boundary layer thickness than thermal boundary layer thickness. So as I've set this equation up right here, it's valid for Prandtl number greater than 1. Right, if I have a Prandtl number less than 1, then I need to come back and rethink what the velocity distribution should be here, right? And actually what I need to do is break it into two integrals. I would break it into an integral where so if we go back one here, I need to break this integral up into two integrals. So the first integration will go from 0 to delta m, and so as long as I'm inside of that boundary layer, that momentum boundary layer, I can use this velocity distribution. But then the second integration has to go from delta m to delta t. So I'm outside of the momentum boundary layer, but I'm inside of the thermal boundary layer. And in that region, I would be, I would have a velocity of U infinity, right? So that's what I've done here. If Prandtl number is less than 1, this is the integration that I should be doing. From 0 to delta m, it looks exactly the same. But once I get outside of that momentum boundary layer, so here from delta m to delta t, instead of having U be some function of y, U is just equal to U infinity, right? And I can still do the problem, but I have to be a little careful over here. For the case where the Prandtl number is a lot less than 1, so Prandtl number much less than 1, then you're in this sort of interesting regime where your momentum boundary layer is extremely thin relative to your thermal boundary layer. So it becomes appropriate to make the approximation that this portion of the integral just basically goes away, right? This region is so thin relative to this region that you can basically just do this the whole time, right? So one thing you'll do in problems where the Prandtl number is much less than 1 is you might just use this approximation where U is taken to be U infinity for the entire integration.